Right now, somewhere in the universe, a star is dying in the most spectacular way imaginable. In a matter of seconds, it will release more energy than our Sun will produce in its entire 10 billion-year lifetime. The explosion will outshine an entire galaxy, forge elements heavier than iron, and send shockwaves rippling through space at thousands of kilometers per second. Today, we're diving deep into one of the universe's most magnificent phenomena, stellar explosions. If you're fascinated by the cosmic forces that shaped our existence and want to explore more mind-blowing astronomical phenomena, make sure to subscribe to this channel and hit the like button. Now let's begin this journey. When we talk about stellar explosions, we're not describing a single type of event. The universe has crafted multiple ways for stars to meet their dramatic ends, each more incredible than the last. The most famous are supernovae, but even these come in different flavors. Type Ia supernovae occur when a white dwarf, the dense remnant of a star like our Sun, steals matter from a companion star until it reaches a critical mass of about 1.4 times our Sun's mass. This is called the Chandrasekhar limit, and when crossed, the entire star undergoes catastrophic nuclear fusion in seconds. Type 2 supernovae tell a different story entirely. These occur when massive stars, at least 8 times heavier than our Sun, exhaust their nuclear fuel. For millions of years, these stellar giants maintain a delicate balance. Gravity pulls inward, trying to collapse the star, while nuclear fusion pushes outward with radiation pressure. But when the fuel runs out, gravity wins catastrophically. The star's core collapses in less than a second, reaching densities where protons and electrons are crushed together to form neutrons. The numbers involved in stellar explosions defy human comprehension. When a massive star's core collapses, it happens at speeds reaching 70,000 kilometers per second, nearly a quarter the speed of light. The core temperature spikes to 100 billion degrees Celsius, more than 6,000 times hotter than the Sun's core. In that fraction of a second, the collapsing matter rebounds off the incredibly dense proto-neutron star at the center, creating a shockwave that tears through the star's outer layers. Recent observations from the Hubble Space Telescope have captured supernovae in unprecedented detail. In 2018, astronomers watched a star explode in galaxy NGC 2525, located 70 million light-years away. They observed the supernova's light curve, how its brightness changed over time, with daily observations for months. This data revealed that the explosion wasn't symmetric. Instead, material was ejected in clumps and jets, painting a picture far more complex than our simplified models suggested. But here's where things get truly mind-bending. During a supernova, the conditions become so extreme that the normal rules of physics are pushed to their limits. Neutrinos, ghostly particles that barely interact with matter, are produced in such vast quantities that they carry away 99% of the explosion's energy. The Kamiokande detector in Japan famously detected neutrinos from supernova 1987A, located 160,000 light-years away in the Large Magellanic Cloud. Only 24 neutrinos were caught, but this was enough to confirm our theories about stellar collapse. The James Webb Space Telescope has revolutionized our understanding of stellar explosions by peering through cosmic dust that obscures visible light. In 2023, JWST observed Cassiopeia A, a supernova remnant from a star that exploded around 340 years ago as seen from Earth. The infrared observations revealed intricate structures of hot gas and dust, including mysterious light echoes, reflections of the original explosion still bouncing off surrounding dust clouds centuries later. What makes stellar explosions truly remarkable is their role as cosmic alchemists. In the extreme conditions of a supernova, atomic nuclei are slammed together with such force that they fuse into heavier elements. This process, called R process nucleosynthesis, the R stands for rapid, creates about half of all elements heavier than iron in mere seconds: gold, platinum, uranium. These precious elements exist only because stars died violently billions of years ago. The violence of stellar explosions extends far beyond the dying star itself. The shockwaves can trigger the formation of new stars by compressing nearby gas clouds. The Crab Nebula, remnant of a supernova observed by Chinese astronomers in the year 1054, is still expanding at 1,500 kilometers per second, nearly 1,000 years later. At its heart spins a pulsar, a neutron star just 20 kilometers across, but containing more mass than our Sun, rotating 30 times per second. Recent discoveries have revealed even more exotic types of stellar explosions. Hypernovae are supernovae on steroids, occurring when extremely massive stars, perhaps 100 times the Sun's mass or more, collapse directly into black holes. These explosions are so powerful they're thought to be the source of long-duration gamma-ray bursts, the most energetic events in the universe after the Big Bang itself. In 2022, astronomers discovered a completely new type of explosion called a micronova. These occur on white dwarf stars but affect only a tiny portion of the surface, lasting just hours instead of weeks. The TESS satellite, Transiting Exoplanet Survey satellite, spotted these brief flashes, revealing that stellar explosions come in more varieties than we ever imagined. The sheer scale of energy released in stellar explosions challenges our understanding of physics itself. A typical supernova releases about 10 to the 44 joules of energy. To put this in perspective, that's equivalent to the Sun's total energy output over its entire lifetime, compressed into an event lasting seconds. This energy doesn't just disappear, it transforms the space around the dying star into a cosmic laboratory where the most extreme physics in the universe plays out. One of the most fascinating aspects of stellar explosions is how they distribute elements throughout the cosmos. When a star explodes, it hurls its enriched guts into space at velocities exceeding 10,000 kilometers per second. This stellar debris, rich with newly forged elements, mixes with the interstellar medium, the thin gas and dust between stars. Over millions of years, this enriched material becomes incorporated into new generations of stars and planets. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in the nuclear furnaces of dying stars and distributed through their explosive deaths. The Spitzer Space Telescope, before its retirement in 2020, used infrared vision to peer through cosmic dust and study supernova remnants in extraordinary detail. One of its most remarkable discoveries was the detection of massive dust factories in young supernova remnants. The supernova SN 1987, A alone created about half a solar mass of dust, enough to make hundreds of thousands of Earth-like planets. This discovery solved a long-standing mystery about where all the dust in the early universe came from. Recent observations have revealed that stellar explosions don't happen in isolation. They're intimately connected to the cosmic web of dark matter and dark energy that shapes our universe. Speaking of which, if you're curious about the mysterious force that's accelerating the universe's expansion and how it relates to stellar evolution, check out my video, Dark Energy. What makes the universe expand? Understanding dark energy helps us grasp why stellar explosions played out differently in the early universe compared to today. The link is in the description below and on the card above. The mechanism that triggers the actual explosion in core collapse supernovae remained a mystery for decades. Computer simulations showed that the rebounding shockwave should stall and fail to explode the star, yet clearly, stars do explode. The solution came from understanding the role of neutrinos. These ghostly particles, produced in incomprehensible numbers during core collapse, deposit a tiny fraction of their energy in the stellar material. This neutrino heating, combined with violent convection and the standing accretion shock instability, revives the stalled shockwave and drives the explosion. The Las Cumbres Observatory, a global network of robotic telescopes, has revolutionized our ability to study stellar explosions in real time. When a supernova is detected, these telescopes can begin observations within minutes, capturing the crucial early moments that reveal details about the exploding star's structure. In 2018, they observed the first hours of supernova SN 2018-0, discovering a brief flash of light that suggested the star was surrounded by material it had expelled in its final years. But not all stellar deaths are violent. Stars like our Sun will never explode as supernovae. Instead, they'll gently puff off their outer layers, creating beautiful planetary nebulae while leaving behind a white dwarf. However, even these peaceful deaths can turn violent if conditions are right. When a white dwarf has a close companion star, it can steal material until it reaches that critical Chandrasekhar limit, resulting in a type Ia supernova that completely destroys the white dwarf. The discovery of pair instability supernovae has revealed yet another way massive stars can die. In extremely massive stars between 130 and 250 solar masses, the core becomes so hot that photons spontaneously create electron-positron pairs. This reduces radiation pressure, causing the core to contract and heat up further, leading to explosive oxygen burning that completely disrupts the star. No remnant is left behind. The entire star is obliterated. Gravitational wave astronomy has opened an entirely new window into stellar explosions. While LIGO and Virgo haven't yet detected gravitational waves from supernovae, they're not quite sensitive enough. They have detected the mergers of neutron stars, the ultra-dense remnants left behind by some supernovae. The detection of GW17817 in 2017, accompanied by a burst of light called a kilonova, confirmed that these mergers are where many heavy elements like gold and platinum are forged. The role of magnetic fields in stellar explosions is only now being understood. Some dying stars have magnetic fields 1 trillion times stronger than Earth's. These magnetars, as they're called, can produce explosions powered purely by magnetic energy. When the magnetic field becomes twisted and reconnects, it releases enormous energy in starquakes that would register 32 on the Richter scale, powerful enough to affect Earth's atmosphere from thousands of light years away. One of the most exciting recent discoveries is the detection of pre-supernova activity. The Zwicky Transient Facility has caught several stars in the act of brightening dramatically in their final months or years before exploding. This suggests that dying stars become unstable and begin ejecting material well before their final collapse. These observations are providing unprecedented insights into the final stages of stellar evolution. The distribution of stellar explosions throughout the universe tells a story of cosmic evolution. In the early universe, when stars were made almost entirely of hydrogen and helium, they could grow much more massive than modern stars. These first-generation stars might have reached 300 solar masses or more, ending their lives in explosions so powerful they left no remnant behind. The James Webb Space Telescope is now searching for the chemical signatures these primordial explosions would have left behind. Supernova remnants continue to shape their surroundings for thousands of years after the initial explosion. The Vela supernova remnant, created by an explosion 11,000 years ago, spans 8 degrees of the sky, 16 times the width of the full moon. Its expanding shockwaves are still heating interstellar gas to millions of degrees and accelerating particles to near-light speed, creating cosmic rays that bombard Earth constantly. The remnants left behind by stellar explosions are some of the most extreme objects in the universe. When a star between 8 and 25 solar masses explodes, it typically leaves behind a neutron star, a city-sized sphere of matter so dense that a teaspoon would weigh about 1 billion tons. These objects represent matter pushed to its absolute limit, where the normal rules of physics break down and quantum mechanics operates on macroscopic scales. Neutron stars are cosmic laboratories where we can study physics impossible to recreate on Earth. Their surfaces have gravity 200 billion times stronger than Earth's. A marshmallow dropped onto a neutron star would impact with the energy of 1,000 nuclear bombs. The matter inside is unlike anything we know, a superfluid of neutrons that flows without friction, possibly surrounding a core of free quarks or even stranger forms of matter that theoretical physicists are still trying to understand. The Neutron Star Interior Composition Explorer, or NISA, aboard the International Space Station, has revolutionized our understanding of these extreme objects. By precisely timing X-ray pulses from rotating neutron stars, NISA has measured their sizes and masses with unprecedented accuracy. In 2021, it revealed that neutron stars are larger than expected, about 26 kilometers across rather than 20, suggesting their interiors contain matter that's stiffer and more complex than simple neutron fluid. But when stars more massive than about 25 solar masses explode, they leave behind something even more extreme: black holes. The moment of black hole formation during a supernova is one of the most violent events in physics. As the stellar core collapses, it reaches a point where not even neutron degeneracy pressure can stop it. The matter crashes through its own event horizon, creating a region of spacetime from which nothing, not even light, can escape. Recent simulations using supercomputers have revealed the incredible complexity of these explosions. The Blue Waters supercomputer ran models showing that the explosion isn't spherically symmetric, but instead develops violent instabilities. Hot bubbles of nuclear ash rise through the star at thousands of kilometers per second, while cold, dense material falls inward. This three-dimensional chaos is crucial for understanding why stars explode successfully rather than simply collapsing into black holes. The chemical evolution of galaxies is driven by stellar explosions. Each generation of stars enriches the interstellar medium with heavier elements, allowing the next generation to form with a richer starting mixture. The first stars in the universe contained only hydrogen and helium from the Big Bang. When they exploded, they seeded space with the first carbon, oxygen, and iron. This process, called galactic chemical evolution, can be traced by studying the composition of stars of different ages. The Apache Point Observatory Galactic Evolution Experiment, or APOGE, has mapped the chemical composition of hundreds of thousands of stars across our galaxy. This survey revealed that the Milky Way's chemical enrichment wasn't smooth, but happened in bursts, likely corresponding to periods of intense star formation triggered by galactic collisions or the accretion of smaller galaxies. Each star carries in its spectrum the chemical fingerprint of all the stellar explosions that came before it. One of the most remarkable discoveries of recent years is the existence of failed supernovae. Sometimes a massive star begins to collapse but doesn't explode. Instead, it quietly disappears as the entire star falls into the forming black hole. The Large Binocular Telescope has been monitoring millions of stars, looking for these vanishing acts. In 2015, they caught one red-handed, a red supergiant star, 25 times the Sun's mass, simply disappeared, likely collapsing directly into a black hole without the fireworks of a supernova. The connection between stellar explosions and life on Earth runs deeper than just providing the elements for biology. Supernovae regulate star formation rates in galaxies by heating and dispersing gas clouds. Too many supernovae, and a galaxy becomes too hot for new stars to form. Too few and heavy elements remain locked in stellar cores. Earth exists in a galaxy with just the right rate of stellar explosions to create a habitable environment, another factor in our cosmic good fortune. Recent studies have shown that nearby supernovae have directly affected Earth's history. Radioactive iron-60 found in ocean sediments and Antarctic snow suggests that supernovae within 300 light-years of Earth showered our planet with debris about 2.5 million years ago. This coincides with a mass extinction of marine megafauna and might have contributed to climate changes that influenced human evolution. The detection of gravitational waves from colliding neutron stars has revealed that these events, called Kilonovae, are crucial for creating the heaviest elements. When LIGO and Virgo detected GW178-17, optical telescopes observed the associated Kilonova AT2017 GFO. Spectroscopic observations showed the clear signature of freshly synthesized heavy elements, including gold and platinum. A single kilonova can produce several Earth masses of gold, along with other precious metals. The Vera Rubin Observatory, beginning operations soon, will discover thousands of stellar explosions per night. This unprecedented survey will capture supernovae within hours of explosion, revealing details about the exploding stars that are currently hidden. Machine learning algorithms will sift through the data, identifying unusual explosions that don't fit our current classification schemes. The physics of shockwaves in stellar explosions involves some of the most complex hydrodynamics in the universe. As the explosion tears through the star's layers, it encounters regions of different density and composition. Each interface reflects and refracts the shock, creating a complex pattern of forward and reverse shocks. Rayleigh-Taylor instabilities, the same physics that creates mushroom clouds in nuclear explosions, operate on stellar scales, mixing radioactive nickel from the core throughout the ejector. The diversity of stellar explosions continues to surprise astronomers. In 2018, the discovery of AT2018 Cow, nicknamed the Cow, challenged everything we thought we knew about how stars die. This explosion was 10 to 100 times brighter than a typical supernova but faded much faster. Located 200 million light-years away, the Cow might represent an entirely new class of stellar explosion, possibly the birth of a black hole or neutron star caught in the act of formation. Stellar explosions serve as cosmic distance markers, allowing us to map the universe's expansion. Type Ia supernovae are particularly valuable because they all reach approximately the same peak brightness. By comparing their apparent brightness to their known intrinsic brightness, astronomers can calculate their distance. This technique, pioneered by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, led to the shocking discovery that the universe's expansion is accelerating, work that earned them the 2011 Nobel Prize in Physics. The Palomar Transient Factory and its successor, the Zwicky Transient Facility, have transformed supernova science by scanning the entire northern sky every few nights. These robotic surveys have discovered rare and exotic explosions that were previously missed. Superluminous supernovae, 100 times brighter than normal supernovae, challenge our understanding of explosion mechanisms. Some might be powered by magnetars, neutron stars with magnetic fields strong enough to erase your credit cards from 1,000 kilometers away. Binary star systems add layers of complexity to stellar explosions. When two stars orbit each other closely, they can exchange mass, altering their evolution dramatically. The more massive star evolves faster, potentially exploding first, and leaving behind a neutron star or black hole orbiting its companion. When the companion star later evolves and expands, it can transfer mass to the compact remnant, potentially triggering X-ray bursts, nova explosions, or even a second supernova. The Chandra X-ray Observatory has revealed the hot, million-degree gas that fills supernova remnants. These observations show how the explosion enriches surrounding space with heavy elements. In the Cassiopeia A remnant, Chandra detected pure titanium, an element that forms only in the innermost regions of the exploding star. The distribution of elements in the remnant tells us about the explosion's asymmetry and the mixing processes that occurred in those first chaotic seconds. Gamma-ray bursts represent the most extreme stellar explosions in the universe. Long-duration bursts, lasting more than 2 seconds, are thought to occur when very massive, rapidly rotating stars collapse. The collapsing material forms an accretion disk around the newborn black hole, launching jets that punch through the dying star at nearly the speed of light. If Earth happened to be in the path of such a jet from a nearby star, the gamma radiation could damage our ozone layer, potentially triggering a mass extinction. The SWIFT satellite has detected thousands of gamma-ray bursts since its launch in 2004. In 2022, SWIFT and the Fermi Gamma-Ray Space Telescope detected GRB 22100-9A, the brightest gamma-ray burst ever recorded. This explosion from a galaxy 2.4 billion light-years away was so intense it disturbed Earth's ionosphere, the first time an explosion from outside our galaxy measurably affected our planet's atmosphere. Recent discoveries have revealed that not all elements heavier than iron come from supernovae. The detection of strontium in the Kilonova AT 2017 GFO confirmed that neutron star mergers are prolific element factories. These collisions create conditions even more extreme than supernovae, densities exceeding atomic nuclei and temperatures reaching billions of degrees. In these conditions, neutron-rich matter undergoes rapid neutron capture, building up heavy elements in seconds. The role of stellar explosions in triggering star formation adds another layer to their cosmic importance. When a supernova shockwave encounters a molecular cloud, it compresses the gas, potentially triggering gravitational collapse and the birth of new stars. Our own solar system shows evidence of this process. Isotope ratios in ancient meteorites suggest that a nearby supernova occurred just before or during our Sun's formation 4.6 billion years ago, possibly triggering the collapse of our natal cloud. Computer simulations have become crucial tools for understanding stellar explosions. Modern supercomputers can model the three-dimensional evolution of a massive star's final seconds, tracking the complex interplay of gravity, nuclear reactions, neutrino transport, and magnetic fields. These simulations require solving equations that describe matter at nuclear densities, temperatures of billions of degrees, and magnetic fields trillions of times stronger than Earth's. The discovery of calcium-rich transients has added another category to the stellar explosion zoo. These explosions produce unusually high amounts of calcium compared to other elements. They might represent the detonation of white dwarfs in binary systems or the merger of white dwarfs with neutron stars. The fact that we keep discovering new types of explosions suggests that stellar death comes in more varieties than we ever imagined. Time-domain astronomy, studying how objects change over time, has revolutionized our understanding of stellar explosions. The All-Sky Automated Survey for Supernovae, ASAS-SN, uses small telescopes distributed around the world to monitor the entire visible sky every night. This approach has discovered supernovae in the act of exploding, catching the shock breakout, the moment when the explosion first becomes visible as it erupts through the star's surface. The elemental abundances in our solar system tell the story of multiple generations of stellar explosions. The gold in your jewelry required neutron-star collisions. The iron in your blood came from type Ia supernovae. The oxygen you breathe was forged in the cores of massive stars and expelled in their death throes. We are literally made of stellar ash, walking repositories of cosmic history spanning billions of years. The technology we use to study stellar explosions has advanced dramatically in recent years. The Atacama Large Millimeter Array, ALMA, in Chile, can peer through the dust that obscures optical telescopes, revealing the cold molecular gas in supernova remnants. In 2017, ALMA detected the first molecules forming in a supernova remnant, silicon monoxide and carbon monoxide forming in the cooling ejecta of supernova 1987A. This discovery showed that supernovae don't just destroy, they also create the molecular building blocks for future planets and possibly life. One of the most profound connections between stellar explosions and human existence involves the creation of radioactive elements. The aluminum-26 and iron-60 produced in supernovae have half-lives of hundreds of thousands to millions of years. These radioactive elements, incorporated into forming planetary systems, provide internal heating that drives plate tectonics and maintains planetary magnetic fields. Without this radioactive heating from ancient stellar explosions, Earth might be a geologically dead world incapable of supporting complex life. The Las Campanas Observatory in Chile witnessed something extraordinary in 2016, the brightest supernova ever observed. Assassin 15 LH shone with the light of 570 billion suns, 20 times brighter than the entire Milky Way galaxy. This explosion challenged all existing models of how stars die. Some theorists propose it might have been powered by a magnetar, while others suggest it could have been a star torn apart by a supermassive black hole, though neither explanation fully accounts for all observations. Polarimetry, measuring the polarization of light from stellar explosions, has revealed that these events are far from spherical. The light from supernovae is polarized because the explosion is asymmetric, with material ejected preferentially in certain directions. This asymmetry might be crucial for successful explosions. Perfectly spherical collapses might fail to explode, while asymmetric collapses create the conditions necessary for the shockwave to successfully unbind the star. The nuclear physics occurring during stellar explosions pushes matter into regimes we can't recreate on Earth. The National Ignition Facility has achieved fusion ignition, but the conditions in a supernova are billions of times more extreme. In the collapsing core, matter reaches nuclear density, atomic nuclei touch each other. The strong nuclear force and gravity compete on equal terms. New particles like hyperons, baryons containing strange quarks might form, creating matter that exists nowhere else in the universe. Recent observations have caught supernovae in the act of interacting with material the dying star expelled years or decades before exploding. The Hubble Space Telescope observed supernova 2014J in galaxy M82, finding evidence that the star had experienced episodic mass loss for thousands of years before its final explosion. This pre-supernova mass loss might be common, fundamentally changing how these explosions interact with their surroundings. The discovery of ultra-stripped supernovae has revealed yet another pathway to stellar death. These occur in binary systems where one star strips away almost all of the other star's outer layers before it explodes. The resulting explosion is weak, ejecting less than a tenth of a solar mass of material, but leaving behind a neutron star. These ultra-stripped supernovae might be the progenitors of the tight neutron star binaries that eventually merge, producing gravitational waves and kilonovae. Stellar archaeology, studying the chemical composition of ancient stars, allows us to peer back at the first stellar explosions in the universe. The most metal-poor stars discovered, like SMSS J0313-6708, have iron abundances less than 1/10,000,000th of the Sun's. These stars formed from gas enriched by perhaps just a single supernova from the first generation of stars. By studying their composition, we can infer properties of these primordial explosions that occurred over 13 billion years ago. The concept of supernova imposters has added another twist to our understanding. Some stars undergo eruptions that look like supernovae but don't actually destroy the star. Eta Carinae, one of the most massive and luminous stars known, experienced such an eruption in 1843, temporarily becoming one of the brightest stars in the sky. The star survived but ejected about 20 solar masses of material, creating the spectacular homunculus nebula visible today. The role of stellar explosions in creating cosmic rays, high-energy particles that constantly bombard Earth, is still being unraveled. Supernova remnants accelerate particles to nearly the speed of light through a process called diffusive shock acceleration. These cosmic rays carry as much energy density as starlight in our galaxy and might play crucial roles in everything from cloud formation on Earth to the evolution of galactic magnetic fields. The High-Altitude Water Cherenkov Observatory, HAWC, in Mexico has detected gamma rays with energies exceeding 100 trillion electron volts from supernova remnants. These observations prove that supernova remnants can accelerate particles to energies far beyond what the Large Hadron Collider can achieve. Nature's particle accelerators dwarf our most ambitious machines. The connection between stellar explosions and planet formation extends beyond just providing heavy elements. The short-lived radioactive isotopes produced in supernovae, particularly aluminum-26, are found in meteorites from our early solar system. These isotopes not only provide dating mechanisms for solar system formation, but also suggest that our Sun formed in a stellar nursery enriched by one or more recent supernovae. We owe our existence to stellar explosions in more ways than we once imagined. Multi-messenger astronomy, combining observations of light, gravitational waves, and neutrinos, has transformed our ability to study stellar explosions. The IceCube Neutrino Observatory at the South Pole, with detectors buried deep in Antarctic ice, watches for the flood of neutrinos that herald a nearby supernova. When the next galactic supernova occurs, IceCube will detect thousands of neutrinos hours before the explosion becomes visible, giving astronomers unprecedented warning to point every available telescope at the dying star. The environmental impact of stellar explosions extends far beyond their immediate vicinity. When a massive star explodes within a star-forming region, it can trigger a chain reaction of star formation and destruction that reshapes entire sections of galaxies. The Carina Nebula, visible from the southern hemisphere, showcases this cosmic demolition and construction process. Eta Carinae and its massive stellar neighbors will eventually explode, potentially triggering or quenching star formation across hundreds of light years. Magneto-hydrodynamic instabilities during stellar explosions create some of the most complex physics in the universe. As the explosion develops, magnetic field lines stretch, twist, and reconnect, converting magnetic energy into kinetic energy. The magneto-rotational instability, first understood in the context of accretion disks, might play a crucial role in reviving stalled supernova shocks. These magnetic effects could explain why some stars explode successfully, while others, with similar masses, collapse directly into black holes. The European Southern Observatory's Very Large Telescope has pioneered the use of integral field spectroscopy to study supernova remnants in 3 dimensions. By measuring the velocity and composition of gas at thousands of points across a remnant, astronomers can reconstruct the original explosion in unprecedented detail. The Vela supernova remnant, studied this way, shows shrapnel flying outward at different speeds, with heavy elements like titanium and iron traveling faster than lighter elements, evidence of the explosion's violent asymmetry. Flash spectroscopy, taking spectra within hours of a supernova's discovery, has revealed what dying stars look like in their final years. The outer layers of exploding stars often show signatures of material expelled months or years before the explosion. This circumstellar material tells us that stellar death isn't sudden, but involves prolonged instability. The star might experience internal pulses, surface eruptions, and dramatic mass loss as it approaches its final collapse. The quest to observe the next galactic supernova has astronomers preparing elaborate alert networks. Statistically, a supernova visible to the naked eye should occur in our galaxy every few decades, but we haven't seen one since Kepler's supernova in 1604. When the next one occurs, it will be the most studied event in astronomical history. Space telescopes will pivot immediately, neutrino detectors will record the collapse, and gravitational wave detectors might catch the asymmetric core bounce. Recent studies of ancient supernovae recorded in historical documents have provided unique insights. Chinese astronomers in 185 CE recorded a guest star that remained visible for 8 months. Modern astronomers have identified this with supernova remnant RCW86, allowing them to study how a remnant evolves over nearly 2,000 years. These historical records, combined with modern observations, provide a time-lapse view of stellar explosion aftermath. The discovery of electron capture supernovae has filled a gap in stellar evolution theory. Stars between 8 and 10 solar masses occupy a gray zone, too light for iron core collapse, too heavy to become white dwarfs peacefully. These stars develop oxygen-neon-magnesium cores that collapse when electrons are captured by atomic nuclei, removing pressure support. The 2018 explosion of supernova 2018 ZD showed all the hallmarks of this long-theorized explosion mechanism. Nucleosynthesis calculations have become sophisticated enough to predict the exact isotope ratios produced in different types of stellar explosions. Each explosion mechanism produces a unique chemical fingerprint. By measuring isotope ratios in primitive meteorites, scientists can determine not just that our solar system was enriched by supernovae, but what types of supernovae contributed. We find signatures of at least 2 different enrichment events, a core collapse supernova and possibly a type Ia or neutron star merger. The role of turbulence in stellar explosions has only recently been appreciated. 3-dimensional simulations show that turbulent convection behind the shock front is crucial for successful explosions. Hot bubbles of nuclear ash rise while cold, dense material falls, creating a churning maelstrom that helps push the shock outward. This turbulence operates on scales from meters to thousands of kilometers, making it one of the most challenging aspects to simulate accurately. Observations of light echoes from historical supernovae have allowed astronomers to study explosions that occurred centuries ago. Light from the original explosion bounces off dust clouds, arriving at Earth years or centuries later from different directions. By observing these echoes, astronomers can see the explosion from multiple angles and at different times, reconstructing a 3-dimensional view of events that happened before the invention of the telescope. The discovery that some supernovae produce too much or too little nickel, 56, has challenged explosion models. This radioactive isotope powers the optical display of most supernovae, decaying to cobalt-56 and then iron-56. The amount produced depends sensitively on the explosion mechanism and the star's structure. Some explosions produce 10 times more nickel than expected, while others produce almost none, suggesting a diversity of explosion mechanisms we're only beginning to understand. Pair production supernovae, theoretical for decades, might finally have been observed. In extremely massive stars, gamma rays in the core become so energetic they spontaneously create electron-positron pairs. This removes pressure support, causing the core to contract and heat up, triggering explosive oxygen burning. The 2016 explosion, SN 2016 IET, showed signatures consistent with this mechanism, pulsational mass loss, followed by a massive explosion that destroyed the entire star. The connection between stellar explosions and galactic evolution becomes clear when we look at starburst galaxies. These galaxies experience intense periods of star formation, creating numerous massive stars that explode within a few million years. The collective effect of hundreds or thousands of supernovae can drive galactic winds, expelling gas from the galaxy entirely. This feedback mechanism regulates star formation on galactic scales, preventing galaxies from converting all their gas into stars. The influence of stellar explosions on cosmic magnetic fields represents one of the least understood aspects of astrophysics. Supernova remnants amplify and twist galactic magnetic fields through a process called the turbulent dynamo. As the explosion's shockwave plows through space, it compresses existing magnetic fields while generating new ones through the Biermann battery effect. These magnetic fields, in turn, affect how cosmic rays propagate through the galaxy, creating a complex feedback loop that shapes galactic evolution. Recent observations by the Sophia Airborne Observatory, before its retirement in 2022, mapped magnetic fields in several supernova remnants using far-infrared polarimetry. These observations revealed that magnetic fields in young remnants can be amplified to strengths 100 times greater than the surrounding interstellar medium. This magnetic amplification might be crucial for accelerating cosmic rays to the extreme energies observed by ground-based detectors. The phenomenon of supernova light curve diversity has become a frontier in explosion research. The Zwicky Transient Facility has discovered supernovae that brighten and fade on timescales ranging from days to years. Some show double peaks, others plateau for months, and still others oscillate as they fade. This diversity suggests that stellar explosions are influenced by factors we're only beginning to appreciate: rotation rates, magnetic field configurations, binary interactions, and the detailed structure of the dying star's interior. Asteroseismology of supernova progenitors has revealed surprising details about stars in their final years. By studying oscillations in nearby red supergiants like Betelgeuse, astronomers can probe their internal structure. These observations suggest that massive stars might have more complex core structures than previously thought, with multiple convective zones and composition gradients that affect how they eventually explode. When Betelgeuse dimmed dramatically in 2019 and 2020, some wondered if it was about to explode, though it turned out to be a massive dust ejection event. The discovery of superkicks imparted to neutron stars during asymmetric explosions has revealed the violence of stellar death. Some neutron stars travel through space at speeds exceeding 1,000 kilometers per second, fast enough to escape their host galaxies. The pulsar IGR J110 14-6-103 holds the current record, moving at approximately 1,100 kilometers per second. These extreme velocities require explosions so asymmetric that more material is ejected in one direction, rocket propelling the neutron star in the opposite direction. X-ray observations of supernova remnants have revealed reverse shocks, shockwaves that travel backward into the ejected material. As the forward shock plows into the interstellar medium, it heats gas to millions of degrees. This hot gas expands backward into the supernova ejector, creating a reverse shock that heats the stellar debris. The interaction between forward and reverse shocks creates complex structures visible in X-rays, including the beautiful shell-like remnants we observe. The role of stellar explosions in dispersing dust throughout the universe has implications for planet formation everywhere. The Herschel Space Observatory detected vast amounts of coal dust in supernova remnants, up to a solar mass in some cases. This dust, composed of silicates, carbon compounds, and iron grains, becomes the raw material for rocky planets. Without stellar explosions to create and disperse this dust, the universe would lack the solid surfaces where life as we know it can emerge. Computational advances have enabled simulations of stellar explosions with unprecedented realism. The Oak Ridge National Laboratory's Summit supercomputer can model the three-dimensional evolution of a core collapse supernova, including general relativity, sophisticated neutrino transport, and nuclear reaction networks with thousands of isotopes. These simulations reveal that successful explosions might require a combination of neutrino heating, convection, and the standing accretion shock instability, a perfect storm of physics operating in concert. The discovery of calcium-strong transients has added another piece to the stellar explosion puzzle. These explosions, producing unusual amounts of calcium, might represent the detonation of white dwarfs in remote locations, far from the galaxies where they formed. How these white dwarfs ended up in such isolated locations remains mysterious. They might have been ejected from their host galaxies through gravitational interactions, or might represent a completely different explosion mechanism we don't yet understand. Time-resolved spectroscopy during stellar explosions has revealed the chemical stratification of dying stars. As the explosion proceeds and deeper layers become visible, the spectrum changes dramatically. Silicon and sulfur appear first from the outer layers, followed by oxygen and magnesium from intermediate depths, and finally iron and nickel from the core. This chemical archaeology allows astronomers to peel back the layers of an exploding star like an onion, revealing its internal structure at the moment of death. The connection between gamma-ray bursts and supernovae has been definitively established through simultaneous observations. Several long-duration gamma-ray bursts have been accompanied by supernova explosions, confirming that at least some GRBs represent the deaths of massive stars. These explosions, sometimes called hypernovae, might occur when rapidly rotating stars collapse, forming an accretion disk around a newborn black hole that launches jets punching through the stellar envelope. Observations of supernova remnant evolution over decades have provided insights into how explosions interact with their environments. The Crab Nebula, observed continuously since Chinese astronomers recorded its birth in 1054 CE, still surprises us. In 2011, the Fermi Gamma-Ray Space Telescope detected massive gamma-ray flares from the Crab Pulsar, releasing energies that seemed impossible for such a small object. These observations remind us that even well-studied remnants harbor mysteries. The discovery of fast blue optical transients represents the latest category of stellar explosions. These events, like at 2018 the Cow, are characterized by rapid evolution, blue colors, and unusual spectra. They might represent the birth of neutron stars or black holes with powerful magnetic fields, or perhaps the explosion of stars stripped of their hydrogen envelopes. Each new category of explosion reveals another way that stars can die, expanding our cosmic taxonomy of stellar death. The impact of stellar explosions on planetary atmospheres throughout the galaxy presents a sobering perspective on habitability. When a star explodes within 30 light-years of a planet with life, the intense radiation can strip away atmospheric ozone, exposing the surface to deadly ultraviolet radiation. Geological evidence suggests Earth has experienced several nearby supernovae over its history. Isotopes in ocean sediments indicate that a supernova about 150 light-years away, occurring 2.6 million years ago, might have contributed to a minor mass extinction event. Neutrino astronomy has revolutionized our understanding of the moments before stellar explosion. While light takes hundreds of thousands of years to escape from a star's core, neutrinos travel at nearly light speed through matter, escaping in seconds. The Super Kamiokande detector in Japan, containing 50,000 tons of pure water, watched by thousands of photo-multiplier tubes, stands ready to catch neutrinos from the next galactic supernova. When it happens, we'll receive a few hours warning before the explosion becomes visible, humanity's first cosmic early warning system. The discovery of Super Chandrasekhar mass type Ia supernovae has challenged our understanding of white dwarf explosions. Some type Ia supernovae appear to come from white dwarfs exceeding the classical 1.4 solar mass limit. These might involve rapidly rotating white dwarfs whose spin provides additional support against gravity, or merging white dwarf pairs that explode during coalescence. This diversity in type Ia supernovae complicates their use as standard candles for measuring cosmic distances. Spectropolarimetry of supernovae has revealed that explosions can be dramatically asymmetric. By measuring how the explosion's light is polarized at different wavelengths, astronomers can map the three-dimensional structure of the ejecta. Some explosions are bipolar, with material streaming out along an axis. Others show evidence of large-scale clumps or one-sided jets. This asymmetry might be essential for successful explosions. Perfectly spherical collapses might fail to explode entirely. The role of stellar explosions in creating the conditions for life extends beyond element production. Supernovae shockwaves can trigger the collapse of molecular clouds, leading to bursts of star formation. Our own Sun likely formed in such a triggered star formation event. Radioactive isotopes from the triggering supernova incorporated into the forming solar system provided heat that helped differentiate planetesimals into cores and mantles, a crucial step in forming terrestrial planets capable of supporting life. Recent observations have caught stars in their death throes, just days before exploding. The Young Supernova experiment uses the Pan-STARRS telescope to monitor galaxies nightly, catching supernova within hours of explosion. Several stars have shown dramatic brightening in their final days, suggesting violent mass ejection just before core collapse. This pre-explosion activity might be caused by silicon burning in the core, creating waves that propagate to the surface, or neutrinos from the forming neutron star depositing energy in the stellar envelope. The phenomenon of supernova imposters, stars that undergo supernova-like eruptions but survive, has revealed the instability of very massive stars. Luminous blue variables like Eta Carinae experience episodic mass ejections that can rival true supernovae in brightness. These eruptions might be caused by the star approaching the Eddington limit, where radiation pressure nearly overcomes gravity, or by pulsational pair instability, where electron-positron pair production causes temporary core contraction. Integral field spectroscopy of nearby supernova remnants has revealed the three-dimensional structure of explosions frozen in time. The Cassiopeia A remnant shows jets of silicon and sulfur punching through the expanding shell, while iron from the core forms isolated clumps flying at different velocities. This three-dimensional mapping reveals that stellar explosions are far from the spherical events depicted in textbooks. They're chaotic, asymmetric, and beautifully complex. The discovery of ultra-long duration gamma-ray bursts lasting hours instead of seconds has expanded our understanding of stellar death. These might come from the collapse of blue supergiants, massive stars that haven't expanded into red giants. The extended duration could result from the time it takes for the jet to punch through the star's extended envelope, or from prolonged accretion onto the newborn black hole. Each new observation reveals another variation in how stars can meet their end. Millimeter and submillimeter observations of supernova remnants have revealed cold molecular gas forming in the ejecta. ALMA observations show that molecules like carbon monoxide and silicon monoxide can form within years of the explosion, despite the harsh environment of intense radiation and shock waves. This molecular formation is the first step toward creating the complex chemistry necessary for planets and potentially life, stellar death becoming the seed of of future worlds. The connection between stellar explosions and cosmic rays has implications for everything from cloud formation on Earth to the evolution of life. Cosmic rays ionize Earth's atmosphere, potentially affecting cloud nucleation and climate. They also cause genetic mutations that drive evolution. The rate of nearby supernovae, and thus cosmic ray flux, has varied throughout Earth's history. Periods of intense star formation in our galactic neighborhood might have accelerated evolution through increased mutation rates. Studies of supernova light echoes have allowed astronomers to perform spectroscopy of historical explosions. Light from Tycho's supernova of 1572, bouncing off interstellar dust clouds, still reaches Earth today. By observing these echoes, astronomers determined that Tycho's supernova was a type Ia explosion, likely caused by a white dwarf accreting matter from a normal companion star. This technique turns interstellar dust into a cosmic time machine, letting us study explosions that occurred before the invention of spectroscopy. The phenomenon of dark supernova, explosions that produce little or no optical light, might be more common than previously thought. These explosions could occur when the dying star is surrounded by thick dust that absorbs optical light, re-emitting it in the infrared, or when the explosion energy goes primarily into accelerating matter rather than producing radiation. Radio and X-ray surveys are revealing a hidden population of stellar explosions invisible to optical telescopes. The molecular complexity found in supernova remnants continues to astound scientists. The ALMA telescope has detected phosphorus-bearing molecules in the Cassiopeia A remnant, a crucial discovery since phosphorus is essential for DNA and RNA. This finding directly links stellar explosions to the chemistry of life. The phosphorus in your DNA was literally forged in the nuclear furnace of a dying star and distributed through space by its explosion. We are not just made of stardust. We carry in our genes the chemical signatures of specific stellar catastrophes. Recent advances in gravitational wave astronomy promise to revolutionize our understanding of stellar collapse. While current detectors like LIGO and Virgo can't yet detect gravitational waves from core collapse supernovae in distant galaxies, the next generation of detectors will be sensitive enough to catch these signals. The Einstein telescope and Cosmic Explorer will detect the gravitational chirp of a collapsing stellar core, revealing details about the formation of neutron stars and black holes that light can never show us. The discovery of pulsational pair instability supernovae has revealed a previously unknown mechanism of stellar death. In stars between roughly 60 and 130 solar masses, pair production causes pulsations that eject shells of material before the final explosion. The star might experience multiple eruptions over thousands of years before either exploding completely or collapsing into a black hole. These pulsations create complex circumstellar environments that dramatically affect the final explosion's appearance. Machine learning algorithms have transformed supernova discovery and classification. The Zwicky Transient Facility uses artificial intelligence to sift through millions of images nightly, identifying potential supernovae for follow-up observation. These algorithms can classify supernovae based on their light curves and colors more accurately than human experts, freeing astronomers to focus on understanding the physics rather than sorting through data. AI has become an essential tool in the age of big data astronomy. The role of stellar explosions in galactic chemical evolution can now be traced with unprecedented precision. The Gala survey has measured elemental abundances for over 600,000 stars in our galaxy, creating a chemical map that reveals the Milky Way's history. Different elements peak at different times in galactic history: oxygen and magnesium from massive stars exploding early, iron from type Ia supernovae coming later, and neutron capture elements from various sources throughout. This chemical archaeology lets us read the history of stellar explosions written in starlight. Observations of superluminous supernovae have pushed the boundaries of explosion physics. These events, 100 times brighter than typical supernovae, might be powered by magnetars, neutron stars with magnetic fields of 10 to the 15 Gauss. The spinning magnetar acts like a cosmic generator, converting rotational energy into radiation that powers the exceptional luminosity. Alternatively, they might result from the collision of massive stars or the interaction between ejecta and dense circumstellar material. The discovery of fast-evolving luminous transients has revealed explosions that challenge our understanding of stellar physics. These events brighten to maximum light in just days and fade equally quickly. They might represent the explosion of stars that have been stripped of their outer layers, the electromagnetic counterparts of stellar collapse with fallback accretion, or entirely new mechanisms we haven't yet imagined. Each new discovery expands our catalogue of ways stars can die. High-energy neutrino astronomy with IceCube has placed constraints on the contribution of supernovae to the cosmic neutrino background. While individual supernovae produce enormous numbers of neutrinos, the cumulative effect of all stellar explosions throughout cosmic history creates a diffuse neutrino background that we're just beginning to detect. These relic neutrinos carry information about stellar explosions throughout the universe's history, providing a new window into cosmic evolution. The interaction between supernova ejecta and planetary systems has implications for astrobiology. When a supernova shockwave encounters a planetary system, it can strip atmospheres from planets, deliver heavy elements and radioactive isotopes, and alter orbital dynamics. Some scientists speculate that periodic supernova exposure might act as an evolutionary pressure, driving biological innovation through increased mutation rates while periodically resetting ecosystems through minor extinctions. Time domain surveys have revealed that some stars experience precursor eruptions years or decades before their final explosion. The progenitor of SN 2009 IP experienced multiple outbursts in the years leading to its possible terminal explosion in 2012. These precursors might be caused by nuclear flashes in the stellar core, pulsational instabilities, or binary interactions. Understanding these warning signs could eventually allow us to predict which stars will explode next. The discovery of intermediate mass black holes in some supernova remnants suggests that stellar explosions can produce a wider range of compact objects than previously thought. These black holes, between tens and hundreds of solar masses, might form from the collapse of very massive stars or the merger of smaller black holes in dense stellar clusters. They could be the seeds that grow into the supermassive black holes found at galaxy centers. Observations of double-peaked supernovae have revealed complex explosion mechanisms. Some supernovae show two distinct brightness peaks separated by weeks or months. This could result from the interaction between fast and slow ejecta, the explosion of a star within a dense shell of previously expelled material, or even two separate energy sources powering different phases of the explosion. Each double-peaked event tells a story of stellar death more complex than simple models suggest. The role of stellar explosions in enriching the intergalactic medium has become clearer with observations from the Cosmic Origins spectrograph on Hubble. Supernova-driven galactic winds can expel enriched gas far beyond galaxies, seeding intergalactic space with heavy elements. This enriched gas can later fall into other galaxies or form new galaxies entirely. Stellar explosions don't just affect their immediate neighborhoods, they influence chemical evolution on cosmic scales. Studies of supernova remnant morphology have revealed the importance of the surrounding environment. The same explosion can produce dramatically different remnants depending on whether it occurs in dense molecular clouds, hot galactic halos, or the low-density intergalactic medium. The Cygnus loop, A massive supernova remnant visible with binoculars shows this environmental shaping beautifully. Its filamentary structure traces pre-existing density variations in the interstellar medium. As we reach the culmination of our journey through stellar explosions, it's time to reflect on the profound truth that connects us all to these cosmic catastrophes. Every element in your body heavier than hydrogen, the calcium in your bones, the iron in your blood, the oxygen you breathe, was forged in the nuclear furnace of a dying star. You are not just an observer of the universe, you are a collection of atoms that have traveled through the hearts of stars, been hurled into space by unimaginable explosions, and somehow found their way to this moment, reading these words, contemplating their own cosmic origins. The future of supernova science promises even more revolutionary discoveries. The Vera C. Rubin Observatory, beginning its legacy survey of space and time, will discover approximately 10 million transient events over 10 years. This flood of data will reveal rare and exotic explosions that occur once per galaxy per century. Machine learning algorithms will sift through this cosmic haystack, finding needles we didn't even know existed, new ways for stars to die that challenge our understanding of stellar evolution. The next galactic supernova will transform our understanding of stellar explosions. Statistically, we're overdue. Supernovae should occur in the Milky Way every 30 to 50 years, yet we haven't seen one since Kepler's star in 1604. When it happens, every telescope on Earth and in space will turn toward it. Gravitational wave detectors will record the core collapse. Neutrino observatories will capture thousands of events. For the first time in human history, we'll witness stellar death with instruments that can see across the entire electromagnetic spectrum and beyond. The philosophical implications of stellar explosions extend far beyond astronomy. These events remind us that creation and destruction are inseparable in our universe. The same explosions that can sterilize planets also create the elements necessary for life. The violence that tears stars apart seeds space with the building blocks of future worlds. In the cosmic perspective, death becomes transformation, endings become beginnings, and stellar catastrophe becomes the engine of cosmic evolution. Recent simulations suggest that the first stars in the universe, composed only of hydrogen and helium from the Big Bang, could reach masses of several hundred suns. When these primordial giants exploded, they initiated the universe's chemical enrichment. The James Webb Space Telescope is now searching for the signatures of these first stellar explosions, preserved in the light of the most distant galaxies. Finding evidence of population 3 supernovae would complete our understanding of how the universe transformed from pristine hydrogen to the element-rich cosmos we inhabit today. The connection between stellar explosions and human consciousness represents perhaps the deepest mystery. The complex chemistry that enables DNA, proteins, and neural activity requires elements forged in different types of stellar explosions. Carbon and oxygen from massive stars, iron from type Ia supernovae, and heavier elements from neutron star mergers all had to come together in just the right proportions on a planet at just the right distance from a stable star. We exist because countless stars died in precisely the right ways at precisely the right times. Future technologies might allow us to predict stellar explosions with greater precision. By combining asteroseismology, neutrino detection, and gravitational wave astronomy, we might identify stars in their final years or even final days. Imagine receiving an alert: Betelgeuse will explode within the next decade. Such predictions would allow unprecedented preparation for studying these events and understanding the final stages of stellar evolution. The role of stellar explosions in the universe's ultimate fate cannot be overlooked. As cosmic expansion accelerates due to dark energy, galaxies become increasingly isolated. Star formation will eventually cease as gas supplies are exhausted. The last generation of stars will explode with no new ones to replace them. These final supernovae will be the universe's last hurrah, the final injection of heavy elements into a cosmos sliding toward heat death. We live in the universe's stellar epoch, a brief window when stars shine and create complexity through their deaths. The diversity of stellar explosions continues to expand as our observations improve. From magnetar giant flares that can affect Earth's atmosphere from thousands of light-years away, to failed supernovae that collapse directly into black holes without fanfare, to superluminous events that outshine entire galaxies, each new discovery reveals another chapter in the story of stellar death. The universe has crafted more ways for stars to die than our imaginations could have conceived. The search for gravitational waves from supernovae represents the next frontier. The Einstein Telescope and Cosmic Explorer, planned for the 2030s, will detect the space-time ripples from core collapse, revealing the dynamics hidden beneath opaque stellar envelopes. Combined with neutrino detection and electromagnetic observations, we'll have a complete picture of stellar death, from the nuclear reactions in the core to the shock waves tearing through the surface to the enriched gas expanding into space. As we conclude this cosmic journey, remember that stellar explosions are not distant, abstract events. They are intimately connected to your existence. The screen you're watching, the air you're breathing, the neurons firing in your brain as you process these words, all exist because stars died. You carry within you the legacy of cosmic catastrophes spanning billions of years. Every atom tells a story of stellar birth, nuclear fusion, and explosive death. The next time you look up at the night sky, see it differently. Those points of light aren't just distant suns, they're future element factories, cosmic alchemists waiting to transform simple hydrogen into the complex elements that make planets, life, and consciousness possible. Some of those stars will explode tomorrow, some in millions of years. Each explosion will add new chapters to the cosmic story of creation through destruction. We are stardust contemplating stars, stellar ash, capable of wonder, the universe becoming aware of itself through beings forged in stellar explosions. This is not poetry, but literal truth, the profound connection between the largest and smallest scales, between cosmic violence and the gentle complexity of life, between stellar death and human consciousness. In understanding stellar explosions, we understand our own origins and our cosmic heritage. The universe has spent 13.8 billion years preparing for this moment, when stellar debris organized into beings capable of understanding their own origins. You are the universe's way of comprehending stellar explosions, of marveling at its own creative destruction, of transforming cosmic catastrophe into conscious appreciation. In that understanding lies both humility and grandeur. We are small and temporary, yet we carry within us the history of the cosmos, written in elements forged in the hearts of dying stars. This is the legacy of stellar explosions, not just the elements they create or the energy they release, but the possibility they enable, the possibility of matter organizing into life, of life developing consciousness, and of consciousness understanding its own cosmic origins. We are the universe's memory of stellar explosions, their most profound consequence, and perhaps their greatest achievement. In knowing this, we complete a cosmic circle billions of years in the making, from stellar death to conscious understanding, and back to wonder at the magnificent catastrophes that made us possible. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Will we ever leave our solar system? In this video, we explore the science, technology, and human challenges behind interstellar travel and humanity's quest to reach the stars. See you there.